My excuses. I got just now. I got interrupted by a delivery at my home. So let me continue. We therefore have the hypothesis of the IPCC is that the residence time may be very short, but the time it takes to readjust to find the new equilibrium can be of the order of centuries. Now, this of course goes against chemistry, secondary school chemistry. They're being some kind of science revisionists. I will just explain why. Because the adjustment time is always equal or shorter than the residence time. And this is simple mathematics that you can prove. But let's go to the definitions. The residence time is how long a molecule stays in a respective box. This is also called the turnover time sometimes. The adjustment time is the characteristic time, the time scale, of reaching equilibrium after a disturbance, also known as relaxation time, or decay constant, or RC time in electronics, as I told you before. Note that if you talk about adjustment time, then the system must be exponential. These are synonyms. Other systems, they don't have an adjustment time because they're not exponential. Then it doesn't make sense of talking about an adjustment time. So if you have an adjustment time, you have an exponential system, you have an RC time, decay constant, relaxation time, and that means it is first order. So when they talk about adjustment time, they talk about first order. Otherwise, there is no adjustment time. That is already first to observe. And how do we do this in signal processing to find the residence time, the RC time or the decay constant or the adjustment time, is we excite the system with a signal that stops abruptly. So you can think about, let me show if I can remove myself again. You can see here on the left, you can have a delta Dirac function, and after that we can see the transient, which is then exponential. Or we take a heaviside, a step function, and we stop it. And then we do find, after that, we can find an exponential transient. Or we take a pulse, which is actually the atomic bombs, as we will see in a moment. And then we can see, all the time, we can see the decay of the system with a certain relaxation time, which we call tau. And this is then the adjustment time. So here, let's take a look now at the kinetics of our atmosphere and take a two-box model. One box, the pink one, is the atmosphere, and the other box is the sink, and I made it blue to hint at that it's probably the ocean, or mostly the ocean. And as we also take Lavoisier, is that the sum of the two, the atmosphere and the sink, they are constant. Of course, we can then add to it from the system, for instance, human emissions, that is to say, anthropogenic sourced emissions, probably from burning fossil fuels. But that is our system. So we have a two-box system that is then following first order kinetics. First, exponential means first order kinetics. Those are synonyms. The flux is proportional to the concentration to the first power. F is K times A. That is how much is leaving the atmosphere every year. And this K is then the kinetic constant from chemistry as we know it. That is just another jargon, but that is the kinetic theory of chemistry. For instance, if we don't have first order models, for instance, that we can have second order, that is possible. Not likely in diffusive systems like our atmosphere and things like this. It's not likely, but if we have second order system, then we would have that the flux is proportional, for instance, to the concentration in the atmosphere squared. And this results then in a power law transient, which does not have a time scale tau. So that doesn't make sense. In a second order system, it doesn't make sense to talk about adjustment times. Now, I also want to tell, and this was also a lot of people didn't get this clear at the workshop, that there is a lot of modeling parameters. They can never be considered as facts, as measured, observed facts. They are all modeling parameters, and there are a few things that are actually observable. And in our system, there are two things that are observable. That is, first of all, the concentration in the atmosphere. I've marked it in green above me. Let me remove myself again. So it is the concentration in the atmosphere, or the density or the total mass in the atmosphere. And it is, which we consider as this is possible to measure, is our emissions, which can be estimated to quite a good degree. These two we can consider observables. All the others are merely fitting parameters or model parameters, and we determine them by fitting our model to the observables, and then we can, if we very much trust our own model, then we say that these are facts, but they're not. Examples are the concentrations in the sink, in the oceans. Nobody knows exactly how much is there, but it seems to be much more than in the atmosphere. And that is already enough to come to very good conclusions, by the way. The other thing is the fluxes from the sink into the atmosphere, because, well, the sink is not there, and you also don't know the residence time in your sink. This residence time you cannot measure. The flux you cannot measure. There is not as if you put a fluxometer between the ocean and the atmosphere. You cannot measure them. You can only model them in your model. And if you trust your model, you think that they are the correct values. So these things we have to be very careful. To summarize this, we have the physics jargon, which is that the flux from the atmosphere into the ocean. I talk now all the way on the left. I think it must be here for you. In the physics, we have the flux from the atmosphere into the ocean, which is given by the density of in the atmosphere divided by the resonance time in the atmosphere. The flux from the sink, the oceans, into the atmosphere is given by the density in the sink divided by the resonance time in the sink. Or in chemistry, we have a system where atoms, molecules from the atmosphere and the sink, they are in a kinetic system, and they have kinetic constants Ka and Ks. Note that the Ks is 1 divided by tau s and Ka is 1 divided by tau a. If we do equilibrium, it's very simple. Then the sum of fluxes must be 0. And this then gives us a ratio between how many molecules or how many moles of molecules are in the atmosphere and in the sink. The ratio between the two is given by the ratio of the kinetic constants, or the ratio of the resonance times. Namely, if the resonance times get bigger, there is more percentage of the molecules in that system. For instance, if the resonance time in the sink is much bigger than in the resonance time in the atmosphere, many more molecules are in the sink relative to the atmosphere. That is absolutely classic chemistry kinetics. So here we can just make actually a simulation. It is, first of all, on the left we have the system once again. It is a simple ordinary differential equation, and this ordinary differential equation you can actually solve analytically, and then you find that the adjustment time of the exponential system, first order exponential system, is given by the reciprocal sum of the resonance times. This is the one in the big red box on the bottom. The resonance times then are reciprocally summed to give the adjustment time. And as you can see, this is like two parallel electric resistances. Two parallel electric resistances never get bigger than each individual resistance. The same for the adjustment time. It is never bigger than any of the two resonance times. So that means that the best you can get is that if the resonance time in the atmosphere of molecules of carbon dioxide in the atmosphere is 4 years, then the best you can get is that the adjustment time is 4 years. So I made a numerical simulation here on the right side, where I put the adjustment, the resonance times in the atmosphere and in the sink to be 1,000 iterations. An iteration we could call a month or a minute or whatever, it doesn't matter. It is about iterations. So I take them 1,000, and as you can see, if both of them are 1,000, then the adjustment time is indicated there by a tau, is 500, which exactly follows this equation of the reciprocal adjustment times. Now the thing is also that if the residence time in the sink is very long, which seems to be the case, at least more than 50 times, in that case the adjustment time is equal to the residence time of the molecules in the atmosphere. So what we expect is that the adjustment time of the system is of the order of 4 years and not centuries. And this is very important, because if the adjustment time is of the order of years, then carbon dioxide is like water. Even if it has strong effects, water has much bigger greenhouse effect, for sure. It is irrelevant because it just rains away. All the water in the atmosphere caused by inserted by burning fossil fuels is just removed by rain. And in the same way, CO2 is rapidly removed and cannot do climate damage. Now, what is the adjustment time? Given the fact that the two are more or less the same, the adjustment time and the residence time in the atmosphere are more or less the same. We have fortunately been done, in this case, fortunately, we have been doing tests, namely the nuclear bomb tests, which inserted a lot of carbon-14 isotope. And you can see here that the adjustment time, it fits very well. I've been doing a fitting myself here above here, and you can see the table. I'm not sure if I'm now visible or not. I should hide myself. You can see here that this adjustment time or resonance time, which is in this case basically the same thing, they're of the order of, let's say, 5, 10, 15 years, which is then too short for the IPCC, because then carbon dioxide would not be a problem, which I will show you in a moment. Their own estimate of the adjustment time is 4 years. I think that's a little bit too short, but okay. I used in a simulation then 5 years. And you can see then what happens if I make a simulation with 5 years. So just make a convolution of all the carbon dioxide emitted that you can see here on the left. And if you look at this and do a convolution, then you can see, let me remove myself, then you can see that with a simulation of 5 years residence time and 50 years residence time in the sink, 5 years in the atmosphere and 50 years in the sinks, then you can see that most of the carbon dioxide that we have been injecting into the atmosphere actually disappeared. On the right side figure, you can see that the green one is the cumulative amount of carbon dioxide we injected in the atmosphere, and yellow is what remains up to that year. And you can see that 90% of all our anthropogenic carbon dioxide has sunk into the sink. It's gone. It cannot do climate damage. And only 10% remained. And this is much too little to do climate damage. Meaning that carbon dioxide is not a problem. And then, if you look at it more carefully, that the increased amount of carbon dioxide in the atmosphere, that is the red box I'm talking about, the amount of carbon dioxide in the atmosphere increment, that then does not have human anthropogenic source. Also very important. So now we start leaning towards that carbon dioxide in the atmosphere is not caused by humans, the increments. Moreover, the idea of a stable pre-industrial 280 ppm value is also not sustainable, maintainable, the idea. Therefore, this is quite damning for the entire IPCC model, because the adjustment time is much shorter than they claim. I want to talk a little, very short to finish this. I want to talk a little bit here about feedback in the atmosphere, because they also say that because of feedback factors, the effect of climate change is much worse. But the assumptions they make is, first of all, that all CO2 changes by humans. Okay, for this point I will admit to that, while in the previous slides I've just showed to you that this is not the case. But let's give them here now again the benefit of the doubt. And they say like all CO2 change is by humans and doesn't have natural causes, and that the greenhouse effect actually exists and has a factor which we call A, and then by feedback they can amplify it. It is very simple to show how this works. Namely, once again, in the, for correlations, you can have a bidirectional correlation that B depends on A and A depends on B. And this way we call feedback. And this indeed can amplify effects quite strongly. And to show you how this works, let me move myself again. On the right, I put a figure. You see here that the effect changing the temperature by an increment in delta CO2, that is A. So if you do by 1 ppm and you increase by 1 degree, you would have delta T, an A, an open loop or a gain. We call it then would be 1 degree per ppm. Of course, it's not so big, but you get the idea that A is what converts an increment in carbon dioxide into an increment in temperature. But what happens now if we put feedback into the system? Namely, that changes in the temperature of the atmosphere or of the climate system will then again change the carbon dioxide concentration in the atmosphere. Note very well, we don't talk about here about changes that the temperature changes methane in the atmosphere, because that is not feedback. Feedback is going back to the original input signal. The changes of methane in the atmosphere caused by heating up the atmosphere, that would be just simply an amplification effect and not feedback. Mind you very well, so we have to talk carbon dioxide, it changes the temperature, and temperature changes carbon dioxide. Otherwise it's not feedback. And you need feedback to have huge amplification factors. Namely, as you can see here again, on the left, we have here again the system. A is called the open loop gain, which is, let's say, this greenhouse effect. And with feedback, you can now see that on the left in the red box, there is the changes in temperature upon changes of carbon dioxide in the atmosphere. It's a very simple mathematical equation. It's A divided by 1 minus A beta. And since this beta is not a parameter that you can actually measure, you just fit it, use it as a fitting parameter to your data, you can actually now explain huge changes in temperature with very small changes in carbon dioxide in the atmosphere. Namely, note very well, if A beta equals 1 or is close to 1, then this entire system can actually go to infinity. And now you understand why they're talking about catastrophe in all the popular media, because the planet can be completely and utterly fried if beta is close to A. And guess what? In their system, beta is very close to A, and we have a very huge factor. And the other thing is, of course, also that if you have such type of feedback, in signal analysis we have this, if you have this system where A beta is 1, or actually bigger than 1 is also possible, then you will get a so-called runaway system, namely that, for instance, 1 ppm will cause 1 degree. This 1 degree will cause 2 ppm. The 2 ppm causes 2 degrees, and then 4 degrees, and 8 degrees, and 16 degrees. You have a runaway situation, and that is why all the alarmists, they talk about an unstable system, and we have only so many years to act before the planet is irreversibly destroyed. And you can see here the first one that started talking about it. You can see here on the left is Mr. What is his name? Maurice Strong from the United Nations. There we go again, the Neo-Communist Institute of the United Nations. And they already said that it is unstable. Vi har 10 år på oss at hede katastrofen. If my Swedish is good. I must have pronounced it here a little bit in a Danish way. Pardon my lack of knowledge of Swedish. But basically, they constantly come with this idea that we have only a certain amount of time to react, because in their analysis they use feedback, and in the feedback they have a feedback factor that is very close to 1 divided by a. In that case, the feedback can even go to infinity and the system is unstable. So the two things, it can get a very strong effect and the system is unstable, and therefore we need to act, because an unstable system, once it has become unstable, then we are completely doomed. However, as you can see, the climate is stable, because every year we make small perturbations, and from summer and winter, and we come back to the previous situation. If it were unstable, even the smallest of smallest, tiniest, as we know from electronics, the tiniest noise signal would put the system off equilibrium. So even if an ant farts somewhere in a forest, then we would go completely out of control by feedback. Feedback then, if it is unstable, it needs very small signals to go out of control. However, the system is stable from observation. It doesn't go out of control, and if it were to go out of control, it would also have gone out of control without human intervention. Then we would have been out of control even without our existence. Now, to put this here in a plot, which the journal doesn't want to process, but you can actually make an estimation of how what your feedback factor is, because look at it once again. We are from on the top in the middle, we have the system where you have X, which is the signal of the CO2, which we're adding. X is what we're adding. Then Z is what we observe in the atmosphere. So that is already with feedback. And then Y is the change in temperature. The idea, of course, is that from Z to Y is the greenhouse effect. That is from how much is in the atmosphere to what the temperature is. And from X to Y is what the effect of humans will be on the temperature. But look at it again. We can then have the entire feedback effect. That is in the, let me remove myself. That is in the red box. You can see that the entire effect of the system of us adding at X, adding some carbon dioxide in the atmosphere will have an effect delta T on the temperature, and that is with that feedback is A divided by 1 minus A beta. But this you cannot measure very well, but what you can measure is the effect from X to Z, namely from how much we put in the atmosphere and how much we see in the atmosphere. And this, in this model of feedback, Z divided by X is given by, in the blue box here on the right, is 1 divided by 1 minus A beta. And as we know, this effect, Z divided by X, is 0.5. As I showed you in the, one of the earlier slides, the effect Z divided by X is 0.5. And if you then look at it, this is only possible if beta is negative. Namely, the Z divided by X is 0.5, therefore beta is minus 1 divided by A, meaning the feedback is negative. The feedback is negative. And if the feedback is negative, then the climate is stable. And we have as much time as we want to address the problem of climate change if it exists. We don't have we don't have 10 years. We don't have, like Prince, now King Charles said, we have only 96 months. We don't have, like Greta Thunberg said, 1.5 years. We don't have 20 seconds, as some kind of sarcastic blog said. We have as much as it takes, because the feedback is negative. Feedback mitigates the greenhouse effect of carbon dioxide. It actually reduces the effect and doesn't amplify it. So, that was my presentation at the Athens Clintel workshop, much longer than there. I had to speed up the presentation there, and my apologies for that. There I had to speak very fast. Now I did it very slow, and I could explain things much more. So let me give you a summary here, that everything can be explained by Henry's law. And in a scientific point of view, this is nice. Henry's law cannot be debunked so far. Be my guest, try to do it. It cannot be done. So as long as the Henry's law stands, then this greenhouse effect, even if they claim they have a consensus, which doesn't matter, that is actually then not the unique model that can explain the things. Actually, it cannot explain the things. There's so many things that are wrong. But in the Henry's law, nothing is inconsistent with it. Everything is consistent with Henry's law, meaning that the carbon dioxide is the result of the temperature and not its cause. We can see that all the carbon dioxide at various timescales, everything is okay. The transient behavior and delay between temperature and carbon dioxide, everything makes sense. The contemporary data, the data of 800,000 years of Al Gore, everything seems to make sense. Remember the effect of carbon dioxide, the effect that we see the carbon dioxide in the El Nino and La Nina years of when the sea surface temperature is changing. We see this. We can understand actually also we can understand the kinetics very well. Everything makes sense. Henry's law is very simple. It's testable in a laboratory. And then by Occam's razor, we should actually use the simple model. While the greenhouse effect cannot be tested and doesn't seem to make sense in any sort of way. The greenhouse effect is the wrong magnitude. The greenhouse effect, according to Knut Angström, already in the beginning, said it was measured it in a tube of carbon dioxide. He said that after 80 ppm, it saturates. The effect saturates. As long as you have other windows in which radiation can be emitted by the planet, then the window of carbon dioxide, when it's blocked, it's blocked. If you put 80 ppm, it's basically blocked. Then doubling it is like putting a double curtain on your window. It doesn't make sense. It doesn't block out any light. It's strange. It has different correlations at different timescales, which doesn't make sense. The greenhouse effect. There's a need for a very critical feedback parameter that cannot be determined based on reasoning or measurement. It is just very strange coincidence that it is exactly the factor that would make the greenhouse effect very strong, and on top of it, that it is exactly in this way that the climate will be unstable, which is too much of a coincidence. While in fact we can clearly see that if you assume all this greenhouse effect, then the feedback factor must be negative. There's only one reason only why the greenhouse effect is considered in our society. Only one reason, that's politics. It is a joint belief fight system. It is fascism. It is climate fascism. There's no other word for it. I cannot say it softly here. It is a thermodynamic optimization called joint belief fight. And as has always been, to fight against the system is very bad for your thermodynamic machine. You basically wind up in a gulag or in a concentration camp, which is not good for your genes. That is why genetically now most people, they welcome fascism. Only a few people can stand up to it and continue to do science, which always goes against the powers that be. Okay, so I thank you for your attention. It was a little bit longer, but I hope that you enjoyed it. See you in another video one day. Cheers.